Okay, hi everybody. 5 in the afternoon. I'll just introduce Dr. Paul Billette and then let you get on with it. So you've met him 2 weeks ago, but I'll introduce Dr. Paul Billette again. He's a software and algorithms team leader at PlotLogic, and he's a highly experienced software and mathematics professional. We're very lucky to have Paul teach this course for the fourth year in a row and help co-create it. So you'll be going on to units 2, 3, and 4 with Paul, and you'll notice a bit of a change of pace and a change of depth. So the boot camp with me in the past 2 weeks was attempted to be elementary and just touch basic things, and we took our time on one thing or another. But you'll notice that the volume and content of things that will come with Paul would be slightly bigger. Make sure to stop Paul where you see fit and ask questions. And also, this is probably a reminder call for everybody to make use of the support practicals if you see fit. It's a great place to just work on your projects, homeworks, because you've got an experienced tutor there. You can also pick Paul's brain in the consultation hour every Wednesday, 7 p.m. in the next couple of weeks when he's teaching. And yeah, thanks again, Paul, for taking the course and leading us.
Thanks for introducing me, Ani. All right, so yeah, change of pace, hopefully not too drastic a change of pace. Hope everyone at home can hear me. Yeah, so I'm Paul. I guess I asked before if you want my introduction at the start or at the end. I can give you a little bit at the start and I'll give you some pretty pictures and stuff at the end. So I guess my career is a bit wonky. I've had a bit of a weird path, but undergrad I was maths and physics, not like I imagine most of you guys are. Did my PhD in engineering, but applied maths really. I was just lost at the time. So yeah, and then I did a postdoc for a couple of years, and then I had kids, and then I needed money, so I went out and got a job. And the way that's tended to go is I've worked at a series of startups. So the first one was a place called Rome's, and you've heard from Megan already, I think. Is that correct? How was Megan's talk? Was that super cool? Yeah. Yeah, so I guess your next lecturer you're going to get, who's an industry lecturer, is Claire. So Claire and I have known each other since the dawn of time. We worked there right from the beginning and kind of left at about the same time. I think I worked there for 7 years or so. And then after that, I left to work at another startup called Alara, which is the other lecturer who's not doing it this year, Andy Ferris. You might have seen his lecture notes. He's a really smart guy. He also worked at Rome's. I poached him to come and work at Alara, and then I left and went to another startup, which is PlotLogic now, and I work in hyperspectral imaging at the moment. So very similar to Megan's stuff. It's just like, imagine a camera that can see 500 colors instead of pouring all 3. So trying to work out you get a lot more information from the deep color channels if you can do that sort of stuff. So I think personally, I would say sort of frame myself as an accidental software engineer. I had no intention of ever doing it. I think I started computer science in first year, and it was the first course I dropped because I thought, I hate that. I never want to do that. And of course, that's what I end up spending my life doing now, just because it goes that way. And I loved maths, always loved maths, and I always loved applications of maths. And so there's this nice crossover, like this is kind of where we're going to start with this basics one. So this is a preamble to that. Analysis is really hard. Like pure maths is really hard. I don't know, maybe you feel this way too, but this path they teach you when you're weaving through undergrad is like, they show you the easy stuff. You try and go off that little path a little bit and everything gets really hard really quickly. So it's amazing the tool we have of computers, and we can, get lots of intuition about problems and stuff that we can't do analysis for. So going to start you off with this. How's everyone feeling with Julia so far? It's like, yay, no. Anyone hates it? No, you're all good people then. That's cool. It's another one, yet another one. It's kind of nice for mathsy stuff in a way that you probably won't appreciate yet. I think by the time you get to like unit 5, where you've got Claire coming in to talk to you about like some of the deeper stuff in the language, you might start to see how it fits in. But at this level, you're just scripting. We're just scripting. I'm just going to muck around for most of my stuff, I'm just going to be either in VS Code or a REPL session. Happy if I say a REPL, what that means? Oh, you're all.
Not really. I don't know what
the acronym. Yeah. Does anyone know what the acronym is for REPL? Yep. Yeah. So read, eval, print loop. So lots of languages have this. Like, so anyone is anyone like, is this, this is their first language they've ever learned? I've got a couple of people there. Who's done some other ones? Who's done heaps? So what's another one with a REPL? Do you know, have you, what's that? No, not so much a command line interface. It's more you can evaluate code as you're running it. So like imagine if you're writing C++ code, you compile it and you can't really interact with it. If you're into something like, say, like Node is the other one I think of, if using JavaScript, you can have one, or IPython. Yeah, definitely. R and Python. So particularly something like IPython, but yeah, Python has a read eval print loop. I think they started with Lisp, which is actually another weird language. We won't talk too much about weird languages though. Anyway, most of my stuff, we're gonna kind of ease you into it. So you've seen a bit of syntax. I'll just mostly muck around in REPL and VS Code, and I'll build some little functions and scripts. When we start getting you out into unit 5 and 6 and stuff, you'll start building your own modules and you'll start working on bigger projects. So we're going to kind of ease you up into the scale of things. So that's kind of where we're going. So first 2 weeks, you got a little bit of syntax. I'm going to show you some syntax again. If anything's not clear, please stop me and go, Paul, what's that weird stuff you're doing? More of this stuff works better if it's interactive. You know, you've got all these lectures from the last couple of years online, so just watch those if you don't want to interact. You've got me here, corner me. I might not be able to answer questions, but I'll go off and try and answer it for you later on if you want. Cool. So, as I said, from the command line, Julia. Hey, I got Julia. And Julia 110.4. So, I will basically be copying this guy across here, but we'll just do it. You can watch this. This is always this moment of horror when I have to do live coding in front of everyone. It's like, I don't know if you realize how brave I am having to do this. It's absolutely horrible, but that's okay. Yoni makes a good job of it. So using random. So first thing we're going to do is we're going to generate data. So what I'm going to do for this first problem is we're going to go, imagine you have some data, and we're going to try and find the maximum element as a vector, we're going to go, what's the maximum element in the vector? So we're going to write a little program that does that. So we'll gradually sneak up on the analysis. So we're going to go random dot seed 1, 1, 2, 3, 5, 8. Okay, so anyone have any idea why I might be seeding a random number generator? Is that something you've seen before? Cool. Yeah, that's pretty much right. I would say in my professional career, some of the most horrific bugs I've had are from not doing that. Something crashes and you're going to lose money and you have no idea why it crashed, and all you can do is try and run. When you run it again, it disappears and you never have that problem again. It is the worst feeling because you know it's going to happen again, but you don't know what caused it. So put a bit of determinism in your it's a pseudo random number generator all this time. So if you seed it, it'll always start from the same state. So as you said, if you're debugging, you know, make your life a lot easier. So I'm going to draw, say, let's just say 100 random numbers. And I haven't watched I skimmed through the first 2 lectures. There's only shown you this hint because I'm going to bang on about it every time I do it. If you don't know what a function does, press Shift $R-A-N-D, and it will give you hopefully better and better documentation about what it's actually doing. So this is a random element from array or random elements, blah, 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 from a specified by S. So if I don't give it a set, it's just going to go like how many. So this, for example, this one rand, it's going to draw, if I'm not doing it for mints, if I just go for the default one, which is what I did, it's just going to go uniform random numbers between 0 and 1, pseudo-random. Let's see what happens. So we are going to try and find, you know, if I'm really doing this, you know, in my day job, I would just do this, maximum data, and it'll go, oh, it's 0.8. But it's built in. We're going to do it by hand. I guess I could ask you guys, how do you want to do it? But that would be inefficient. So you just get to watch me and shout out when I get it wrong, because I literally will get this wrong the first time. So we'll go find max. We're going to write a function. So we're going to go max value. So we'll start off with a number that we know we're never going to be bigger than. So we'll start off with -infinity. And then we will go for xx in x if xx greater than max value max value equals XX. Okay. Anyone see any problems with that, or does it look all right? Yep. Oh, you could do that. I always like being specific with the return because I'm dumb and I go back and I look at it and go like, well, what's it going to return? So I always like to be a little bit more explicit and always put the return in, but you don't have to do that, that's for sure. So one of these things, I hope, as I guess Yoni's already said this with the function, you always return the last line by default. Sometimes when you have a bit of control flow in there, it's really confusing about what the last line actually was. So I always like to just write it out. So you can also have multiple returns within, so just to make it confusing. But oh, no data. Sorry, I'm an idiot. So yeah, got the same answer. So cool. Okay, that's pretty trivial. Everyone happy with that? Everyone happy with the syntax? Nothing too hairy yet. Okay, let's make it a little bit harder. And then we're turned into a maths problem. We're going to go like, when we're going through this array one at a time from start to the end, how many times are we going to find a new biggest value given a size of the array? So like that's a pretty simple, straightforward maths question to ask, but it's actually not that straightforward to do the analysis for, I would say. But maybe that's me with my old brain. I've been out of undergrad for years, so actually having to do a maths problem gives me the horrors. But we'll go through that in a bit. But you know what I'm trying to, there's pretty minor modifications to this function, and we can. Sorry, this is going to look a little bit ugly. Count equals 0. Count plus equals 1. So now, if I run find max on data, I get 5 times. So did you see what I did just there? Oh, sorry, I just typed it and I wasn't talking. I forget I'm in a lecture, not at work. So what I've done is I've added a new variable. You can put another line in line by putting a semicolon there. You don't have to do that. It's just easier in the REPL without having to write the whole function again. Just put a count equals 0. So every time I find a new max value, I'm going to go, oh yeah, count plus equals 1. So is that going to be deterministic? If I draw another set of random numbers, what am I going to get? Am I going to get the same answer? No. Oh, just want to do that. So find max, data, 4 that time. Tell me when you get sick of this. 3 that time. Endlessly surprising. So sort of get this hint that's buzzing around. You know, maybe you're going to get, you know, maybe there's some pattern there. Maybe there's some distribution over this you're going to get. So we'll see how the notes did it. Basically, that's the same thing. Okay, cool. So yeah, we've done this thing. If we start with a different seed, we're going to get a different max value and we're going to get a different count. And so the maths question is, on average, what are we going to get? So that seems easy enough or not so easy. We'll just go through what analysis for that would look like. So if we have n data points, we're going to define this indicator function that goes like, if it's the new max, put in a 1. If it's not the new max, put in a 0. If we take the expectation of that, the average over n, that's the number we're going to try and get. You probably won't be lucky and get a nice integer, but you'll get something like that. So observe that blah, 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 blah. And for statistically independent and identically distributed data points, we have the probability that the next value is going to be 1 on I. Okay, so just to be a little belabor this point, if there's one element in the array, what's the chance that that's going to be the biggest element in the array? 1, right? And then for the next one, it's going to be 1 on 2. And for the next one, this is a little bit where it gets a little bit less obvious for me. I think I fell over this last year when I sort of went, hey, it's obvious, it's just 1 on n. So for 3, it's 1 on 3 for the third element. Then when you get to the fourth element, it's 1 on 4. So anyone have any intuition about why that would be? Or is it obvious enough that you don't have to think about it? Yo.
Just get a big number. One of those numbers is the largest.
Yeah. So how would you make this precise? I guess if you're going to turn it into a probabilistic, like to actually calculate that probability, how would you go about it? I would say you can do this, the way I've thought about it, is that if you think of like, I've got n numbers, how many ways can I arrange n numbers? Anyone? N factorial, okay. And so if I take the biggest number out of that and rearrange all the rest of them, how many different ways are there of arranging those guys if that one's taken away? Yeah, so if I'm going to calculate the probability, if I go n minus 1 factorial divided by n factorial, that should be the probability that the next element in the array is going to be the 1. Carry that through, you should get 1 on it. You believe my lies? Yeah, good. Check that out yourself anyway. So that's kind of the logic for why it's 1 on n. This is where it actually gets hairy though, because like as that goes to n, keep covering the microphone, as that goes, n goes to infinity, what happens to that sum? So we're going to sum up. So as we set up here, they're identically distributed. So we're going to go like expected value for 1. It's this, actually, this ends up being this sum. And does this sum go to a fixed value as you go to infinity, or does it convergent or divergent sum? Divergent sum. So you actually want to evaluate it at a finite number of terms. It's actually this thing called a harmonic sum. And some clever people in the 17th century, 18th century, Euler-Mascheroni constant, you can figure out that this 2 order 1, this is what, I'm not going to do this bit. I can do the n minus 1 factorial on n factorial, but the harmonic sum goes like this, where it's harmonic sum log n plus this Euler-Mascheroni constant plus order 1 terms. So, and the order 1 terms vanish as n goes to infinity. So you can say approximately this harmonic sum is going to be like log n plus this Euler-Mascheroni constant. Cool. So there we go. That was just for the expected value. So what about like, if you want to make it really hard, like what's the distribution? Like, oh God, I don't want to do that. Like what would actually be the probability distribution over values as you go up? It's one of these things where you go like, I just changed the question a little bit and the analysis gets really, really hard, really, really quickly. Not even sure if there is like a simple expression for what that distribution would be. But thankfully we have computers and we can see what this does. So I'm not going to bother typing this stuff out, but I might talk a little bit about the syntax. I'll put plots up though. Okay. Did you see the using? Is that like, do you see that in the only section? You know, that's including a module. So plots is another module you might want to use. I'll just leave that there for later. We've got some funky stuff going on here. So I'm just going to go here. So you saw you have all this Unicode support, so you can put LaTeX symbols into Julia. That's fine. If you want to make a variable called hot dog, you can. It's got all the emojis. Please don't do that in your assignments unless you want to be annoying, which I can understand. So print line, you've seen that. We've got this little bit of string stuff. It's kind of not natural to do it this way. I would not be doing it that way myself. So just going to harp on a little bit about syntax. I'd probably go, did you see the string interpolation stuff? Okay. So just for clarity, if I don't do this, you're going to get this thing with the ellipsis because it's actually representing like an actual real number as a math constant, not a float 64. We're going to talk about data types later in this lecture, but yeah, so casting it to a float just so you get this finite precision thing rather than getting the big thing. And oh, what is that symbol? I don't know. I'll just say it's gamma. It's probably wrong. Equals. Did you see this stuff if you do this? So yeah, cool. You can do, it's another way you can do it. So there's a million, this is one of the problems when you're coming to a new language is like, there's a million ways you can do things. Not all of them are good. Some of them are interesting. So you'll see me do some lazy things when I'm just typing here. You'll see some good stuff, some bad stuff, hopefully, but similar thing. Anyway, that's just what that is. I just wanted to say about that. Another little hairy bit of syntax is this is an inline function. Have you seen this before? If I do this guy, there's actually quite a lot of syntax going on in this one little bit of expression, on this little expression here. So that's kind of confusing. We're going h, put some parentheses, n equals the sum from I equals 1 on I for I and 1 to blah, blah, blah. So what that actually does is it defines a function. So you've probably seen something more long-winded where it's like function, h of n, return some blah, 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 blah. So blah, blah, blah. You probably haven't seen something like that. You can actually define functions inline. So you can just put the parentheses after the variable and you'll get the function straight away. That's that little bit of syntax. And basically what this little bit, I'm not going to repeat all of this, but what we're going to do is you go, this is the sum, this is that approximation. What do those approximations do? The error gets good as we go bigger. So yay. So that approximation seems like it works. But what's more interesting is we can just run this function multiple times in a loop, and we can actually get like an idea of the distribution over the data. So this is a bit of analysis that like I'd find horrifying if you had to say like, what's the probability distribution as you're changing n for this thing? Just simulate it on a computer and it's really fast. So we'd call that a Monte Carlo estimate. And I'll just run this bit of code in my session and we'll see what happens. Oh, I didn't put a prox h in, but you see don't worry about that, but you'll see there's distribution repeats what happened in the notes. So it's really easy. And this is one of these really powerful things. It's like, there's a bit of analysis that would have taken ages for me to do. I want to see what kind of things going on and get intuition or get some approximate answers. Like doing stuff with the computer is super powerful, particularly like in all branches of science and mathematics. It's a huge deal. Cool. That's my little gentle warm up. Like here's a math problem. What we're going to do in section 2 is I think the next bit, what do I want to do with the next bit? Next bit's going to be a bit of propaganda about why you should care for anyone who's on the fence about like, is coding for them if you're interested. I'm assuming everyone here, does everyone like maths or you just hear suffering and suffering? If that's your case, I can't help you, but I can sell programming to mathematicians as a super useful tool. So you probably had this with Yoni, but I'll go through it again. Assume, just show of hands, who likes Python? Who's used Python and liked it? Who's used Python and doesn't like it? Yeah, I'm with you. It's boring. Should use something weird and exotic like Julia. Yeah, probably done some MATLAB. They still teach MATLAB at uni? Everyone do that? What's MATLAB like? Easy enough? Boo. Yeah, boo. It's like, it's got its place, I think. Is like, if you think like, the history of MATLAB is super interesting because it was a guy teaching a course like this in the 70s and all they had was a Fortran library for linear algebra. And so when I'm going to make it easier to do linear algebra, I'm going to make like a calculator for linear algebra for students so they can actually do the course and not have to worry about programming low-level stuff. And the guy, Cleve Moeller, I think his name is, I'll get that wrong, came up with this programming language. So the way to think of it, well, I don't know what it's turned into now. I haven't used it for 15 years, but it was like, think of it like a calculator for linear algebra. And then it's kind of awesome because it's like, you couldn't do that before. So it's a cool tool, just, it's not easy to do a big program in, and, it's commercial, which is boo. I think that's the worst thing. How about R? Everyone used R? What do you think of R? You like it? Yep.
It's just simple. It's open source.
Yeah. Yep, cool.
I think it's limited, right?
Yeah, it's got its place. The ecosystem, it's like Python. The ecosystem is amazing. Like if you want to do a stats thing, you can kind of grab it from R. Like, yep. Yeah. So it sounds like that. You've got a couple of people, it's the first time languages. Like this is the problem when we do this course is like, we're going to have some people, it's the first time and they're going to go, oh God, all this new stuff. A bunch of other people have been programming since they're 8. I'm not really talking to those guys. They can go away. But, we've got this bimodal distribution. We're going to try and bring it together by the end of the course. You wouldn't do the course if you knew all the stuff already. So hopefully we'll learn some things. This is basic stuff, so where you should be is like, you've written some stuff, hopefully in the first 2 weeks, you do some simple scripting stuff in Julia so far. You know what a computer program is, and you can do little control flow, if I say that, like conditionals with ifs and elses and such. Anyone program for fun? You got a bit of calculus and linear algebra. So hopefully that's where we're at. So here's where we come to the propaganda, where I'm going to try and convince you that computers are great and you should worry about it. Like it's a valuable part of your education. So I'm going to start out, I always bring this prop for this thing. I have this old ancient book that's, I think it's 130 years old, maybe. Yeah, it was in 1892 this book came from. So this is a really confusing book. It's really confusing that I own it. That just shows you what type of person I am. But something you don't think about these days of how hard it was to do anything a long time ago. So what this book is, it's called a Ready Reckoner. Has anyone heard of one of those? Nobody's heard of one of those. So, or you have? Yeah. So what this was, who knows how pounds, shillings, and pence work? Like how many shillings to a pence or whatever. You actually know, I've forgotten. So yeah, so it's this annoying problem back in the day. So if someone was a shop owner and someone goes like, okay, this thing's going to be 2 pounds, 3 shillings, 8 pence, and you need to do a fraction of it for doing change and things like that. So all this book is a giant table of 3 shillings, 4 pence, blah, 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 and fractions down the side. So the whole book is just for a shopkeeper to go through. And it's pages and pages of fractions because most people were, I guess, not whatever the numeracy version of illiterate is like most people couldn't do the sums. You know, they didn't have calculators. It's a calculator. Yeah, that's right. And so we have this amazing technology now, like everyone's got this amazing bit of technology in their pocket, hopefully, maybe not, maybe it's not good, but yeah, things like this used to have to exist. And it's kind of amazing that they, you know, and we've forgotten because it's all gone. Like we don't need that technology anymore. Calculators supplanted a whole publishing industry of having these things, these books. Feel free to have a look. You can grab it, just don't rip it to bits. Kind of loaded question. I've got this picture here of, actually I didn't check. Here we go. So computers early on was actually a room full of people. So they were doing computation. So I think this is interesting for me. So one of the first open source things I did for Julia was a thing called the linear assignment problem. So this is another simple sort of maths problem. You go like, imagine we've got a factory and we've got like, you know, n machines and m people. And someone's gone through and they've gone like, well, John's really good on machine number 2. He takes this long to make a widget. And Mary's really good on machine number 3, and she takes this long for the widget. So if you make a matrix of all those costs per person to job, and you have a constraint that I'm going to put one person on one job, and I want the minimum sum. That's called the linear assignment problem. That was, I'm writing a package to do linear assignment problem. I had a problem at work I needed to do, and I went like, oh yeah, I'll go implement that because it's not in Julia yet. That seems like a fun project. And I read the paper. I think I got the paper here. This funny Monk-Res algorithm. So it's not that old from an old guy. 1957 was when this paper was published. And you have this really strange notation in the paper where it's saying like, go to this column, prime and star. And what they're actually talking about is instructions for these sorts of people to actually do it by hand. The algorithm is an algorithm for people to do by hand to solve this problem. And you go to the paper and it's like, why are they saying prime and star? And the notation's really, really strange. And then you click and you go like, oh, it's for people. It's for people to do. So again, computer's not a simple thing. So I'll go back to here. Yeah. This guy, it's like, anyone know what this is? Probably do. Anyone who watches documentaries or too much YouTube? Yeah, so this is even before that. This is 2,000 years old. This was found in a shipwreck off Greece, and it's called the Antikythera mechanism. And they were really confused about what it was, and they did X-rays and stuff. And then they worked out, oh, it's working out like it's like a calendar thing. It's like a mechanical calendar. So that long ago. So computers kind of like, you know, it's less narrow than what we think it is. It's like a device for doing computations that are useful and long, long history. So that's the Antikythera mechanism. This is probably the one you're thinking about, the difference engine. Yeah, so this is Charles Babbage. So this, anyone heard of the difference engine? Do you know what it was for? What's that? What was it intended to do though? It was more specific than that. Oh yeah. It was more weird than that and probably more mathsy than you'd think. Okay. Yep, by quadrature with interpolating polynomials. So it was actually for calculating the coefficients for interpolating polynomials, the first one was. It's like, whoa, what? So kind of strange, right? And that's that one. So not to be too, kind of like all this stuff. So I'm going to get this one. Karakuri is a thing from Japan, which is kind of interesting. These are little automatons and they will make tea and do calligraphy, and they're kind of cool if you go and look up videos of them. There were like all these histories of automatons, and people, interesting one that I find interesting is people like Descartes and Leonardo da Vinci made automatons too. So they used to make little robots, little wind-up robots that would do a thing. And so a really broad definition of computation here, I'm thinking more of like clockwork, where it's doing modular arithmetic. So, you know, winds up this far, does a thing, increments a counter. Another one that's cool, go for this guy. Has anyone seen one of these before? You have? Encoder. Yeah, so this is the Apollo era sort of technology of when they were doing sums for the rocket. They would use this as a mechanical calculator. So I think the guy designed this in a concentration camp in World War II. So if you ever think your life's hard, I just think other people have it harder. Yeah, I always want one of these, but they're getting really expensive. It's not going to be a chance. Another one that's kind of cool as like not a digital computer is this is one of these guys is an analog fire control device from a bomber in World War II. Another thing, they would, you know, it's a terrible application of cool technology of like, if I'm flying along this fast and the wind's coming this way, when do I drop the bomb to hit the thing over there? They had calculators for doing all that stuff. So complicated mechanism inside doing that stuff. Didn't actually work that well, these ones. They spent a lot of time, but they were kind of terrible. But that's an interesting bit of technology. So I think that's all that stuff. And yeah, back to this guy. Of these things that we used to have, there used to be books and books of tables of logarithms and trigonometric functions. And even back when I was where you are, maybe you can have this one of like, anyone done Laplace transforms yet? Fourier transforms? Yeah, any of that stuff? It used to be in the library, there would be books of tables of Laplace transforms and stuff where I think the story was in the Depression, they get mathematicians to do tables of Laplace transforms, Fourier transforms. Now, if you had to do that stuff, you either do it yourself or you go look up on something like Wolfram Alpha or use Mathematica, have software to do it. All ancient stuff that's gone away because our life's easy. Okay. So this lady here, is it connected with that other machine I talked about? Does anyone know who she is? Ada Lovelace, yeah. So arguably wrote the first program for a computer. What's that? Yeah. Debugged as well, yeah. So like, yeah, it's kind of amazing. So anyway, I've said a bunch of names here. I said names like, oh, we've got Babbage, we've got Ada Lovelace, we've got another name down here, von Neumann, I've got Descartes. What's in common amongst all these people and that difference engine machine? What's like the career choice of these people? They're all mathematicians, yeah. Computers were built for mathematicians, by mathematicians in the first place. And then we let computer scientists get too excited, but got to pull it back. All the initial stuff, all this technology, the first thing was for helping with mathematics. It was not for freaking selling ads to people for stuff they don't need. It's for doing mathematics. So cool. So yeah, I think I wanted to say that's a little bit of propaganda for like why I think you should care. And like It's really useful. So not going to talk about this too much because I'll just embarrass myself by lack of knowledge. So most of the computers today have this thing called a von Neumann architecture. That is, what do I want to say about that? I'll go back a little bit. First thing I want to say was like narrow definition of a computer, of like a digital general purpose computer is what most people think about when they say computer. Scope of a computer is a much bigger thing of doing sums. There's analog computers, there's less not general purpose computing, which is pretty common. So, but then there's weird history, like, you know, if I say like a GPU is not originally a general purpose computer, but now people use it for general purpose computing. So there's GPUs. In the initial bit, they were just for doing graphics calculations fast. There's a whole world of microcontrollers and things like that that have different architectures. But most of the time when I'm talking about computers, we're going to talk about digital general purpose computer. And even this will, I'll try and point this out in this course as we go through it. There's bits of it that seem weird, and you got to keep in your mind that this stuff was just invented at a point in time. And there'll be weird things about, and when I go into the next section, we're going to have, when I go into the next section, I'm going to go a bit about bits and addition and how we represent numbers. That's going to be second half of this lecture. There's going to be stuff about the way that we represent things on a computer that seem a little bit weird, and they're actually tied to the hardware. So in mathematics, abstractions are kind of nice and beautiful and you can build on them. In computers, the abstractions always kind of leak a little bit, and the detail of something underneath pops up through, and you go, why am I doing this weird thing? And I'm doing this weird thing because this weird thing over there is happening, and I have to kind of catch it. That's kind of a thing to keep in mind. And if you find something strange, it's usually a reason, it's usually a historical reason, and it's actually usually a good reason. Sometimes it's not a good reason, but that's kind of what you have to work with. It's one of these things people find hard. Yeah, so you're going to have von Neumann architecture is shared data and instruction set in memory. So there's this thing called the von Neumann bottleneck about scaling for computers because CPUs got too fast. Yeah, so you're going to have memory, slow storage. That's kind of a spectrum these days of what's memory and what's external storage, because you've got caches and things like that. We'll see some evidence of caches and stuff when we go through a little bit about how things are laid out in memory on the computer. So we're going to go into that a little bit. Not that I expect you to know this stuff. It's just, I think it's good to see it so you can understand about things going a bit wrong. Yeah. Yeah, and again, higher order instructions all the way up. So you've got a CPU and there'll be an operating system. What operating system most people are running? I'm going to guess Windows. Show of hands for Windows. Anyone not running Windows? Who's doing, what are you on? Ubuntu, yeah, like me. What about you? Mac? Yep, okay. Anyone doing something super weird? Nah, no one's doing something super weird. That's not exciting. Yeah, so I guess I guess this is one of the things with this course. Has the installation of Julia gotten easier? Like, has anyone had any big problems installing it, or is it pretty smooth? Yeah. So yeah, Windows Terminal was the solution in the end. I think I saw looking on EdStem. Is that what everyone's onto? Yeah, like you got this, another annoying thing to realize is most of the people who do the development will be on a Unix type system, like a Mac OS or Linux, some flavor of Linux. So it'll probably work on Linux or Mac. And then when you go to Windows, you might have problems. So sorry, everyone. That's just the way it is. And it's kind of this thing of like, we're in this course, we'll show you a little bit of command line stuff in Bash, nothing super serious, but when you go out, if like my day job, most of it's doing that. All servers are basically Linux flavor these days. So that's kind of the way it goes. Again, this is mostly just to point out Turing, another mathematician on the early history of computers. So someone, famous mathematician doing work on computers. I'm not going to talk about Turing machines in this course and finite automata. Basically, proofs about limitations of computers. Blah, 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 blah. History, main historical propaganda point is they were all mathematicians. You're mathematicians. You should learn how to program. Okay, this is, I guess, professional development stuff of who is a software developer. What's software development like in the wild, and what kind of person's this programmer? Yeah, you're going to have people who's joined like who's a CS person, like who's actually doing interest into computer science as a number one priority. Split on the fence between maths and computer science. Are you more on the software engineering side or the computer science side, would you say? Yeah, that makes sense for maths. And like, I'm going to say this for all you, we're all kind of in the same tribe, I would say, of like, you're interested in the structures and the stuff and not so much the details of how it's particularly implemented. That's reflected in the workforce. People like us, when you go out, like if you've got a really strong software background, you'll fit right in, you swim like a fish. Other ones, they never quite know what to do with them. They were calling them data scientists for a while, or machine learning engineers, who knows what. To name changes every 20 years or so, 10, 20 years. But there's always been this two culture thing in programming of like people who can do hard analysis but aren't necessarily the best on the tools, and then people who are really good on the tools and get really angry with those guys. But you can't get rid of those guys because they're writing all the stuff that makes money. So it's kind of interesting. Things to learn. It's like, I would say a lesson from my own time here, if I think again, is like the way we set up university education is a bit wrong because the artifacts you make, you're just trying to pass the test. So if you're doing big homework, I was in your position just doing the first big homework or one of the projects, I just smash it out, get the answer. I don't care about the thing, I just care about the result. Most people in this sort of sciences are results-oriented people. You got to try and flip that on its head when you realize what software is for and how long it lasts. Like one of my horrors of like things I wrote when I was 20 are still running in production and make other people lots of money, not me. Millions of dollars are going through some code I wrote when I was in my 20s and I had no idea what I was doing still, and they haven't gotten rid of it. And I wish they had, I wish they'd rewritten it. This thing lasts forever, and you meet people when you're older and they go like, oh, you worked on that code base. Like, oh God, it's a shame. Like this stuff can last a really long time, particularly for the type of work you people are likely to be doing. And so I had two little aphorisms. I'm going to get it wrong. Attribution, I should have put the attribution here. It's like code is read more often than it's written. Not always true. Sometimes you just do a hairy math thing and no one just put the lid on the box and never wants to look at what it's doing inside as long as the results are good. But usual case is that people are going to go over it again. So it's really an expression of communication. Communication is a big deal. So when you're trying to write stuff, this is going to be like, you're all too early for this to resonate, but like there's ugly code and there's nice code. Later on in this unit 2, I'll show you something that I think is clever and ugly. That's one of the things I'm going to go point at and make fun of. Communication's pretty important. And two hard things in computer science, cache and validation and naming things. So when you're writing your stuff, think of it just like in a mercenary fashion, make it easy for the tutor to mark your stuff. Like you'll get a better mark, even if it's wrong, if it's comprehensible. I mean, that's a lesson for everything. So complaints with software engineers entering with mathematicians is like, there's this big box of yuck that it's hard to follow. Please don't be like that. Try and think about how to structure it. It's hard, I can understand that, particularly when it's a hard problem. Yeah, code, this is getting better than it was. It's way better now than it was when I was an academic. The code is an artifact of doing research, and like outside academia, that flips. You just do the code to write the paper. Now people will put the code on GitHub, reproducibility. It's fucking awesome. Oh, it's very awesome. It's really good. It's much better than it used to be. Yeah, and it's an artifact itself, and it's a communication thing. And like we're working in these higher order languages for that reason in particular, that it's really easy to, it should be easy to follow. The ideal language, no one's got there. Julia's not it. Python's not it, but they're pretty good. Should be easy to follow. You should be trying to express yourself a little bit. Another thing I want to say is like, not obvious to you guys, but I mean, think of this book as like, 130 years ago, most people couldn't do sums. You guys are all able to do a thing most people can't. You're going to bring a lot of value to people if you can get your stuff down and make it nice and have people use it. So, so it doesn't feel like it at the moment. I can understand that as an undergrad, but when you're out, you'll be able to do things that are very, very good. Yeah, that's the propaganda bit done. Any questions on any of that stuff? I think I will take a very short break because I'm not used to talking this long, just 5 minutes. And then I'll start again on bits and stuff. If you have any questions, I'll just turn the mic off about homework or anything. Just grab me. That's it. There we go. Okay. All right, I'm drinking in front of people. Okay. So we've got this idea of a digital computer. Sorry, can you hear me all right? Yep, all good. Okay, just checking back online. Okay, so we've got a digital computer versus an analog computer. Analog computer's got this nice property that it can kind of more actually represent the real numbers, which is a thing we'd be interested in as mathematicians. When we go to digital computers, the fundamental technology is a transistor, which is like a kind of switch. And it has discrete levels. So in a computer, it's turned into an electrical engineering class. So I can't say if it's going to be right. I'll just say some words and you can go, yeah, that sounds good. You're going to have a high voltage level and a low voltage level given the semiconductor material that goes through it. So it can either be a low voltage or a high voltage. So on a register, all you have in a digital computer is these registers, and it's gone on a low level, it's going to go like on, off, high, low, high, low, high, low. So you have some code, and each one of those is a high or a low. You can interpret as a 1 or a 0, a true or a false. Actually doesn't mean anything, like, right? Like it's just a high or a low voltage. How the program uses that is what it means. So it doesn't mean anything of itself. How we compose these things. And the fundamental one is a bit. And I always get these ones wrong. A byte is super weird. I encourage you to nerd out about history and look at the byte. A byte meant different things in different bits of time. Now it means 8 bits. At different times in history, it meant 5 and 4 and 7, just random things early on. Some idea that you want some organization of these things, and like, what's a nice chunk that you could think about? They called that a byte. Some people say 4 is a nibble or something, whatever. So you've got at a low level on this computer, you're going to have this register, and it's going to be high, low, 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 high, high, low, high, low, low. It's code changing as you mutate it. It's going to give you different things. So if you have 8, hopefully this is super obvious, but if you have 8 bits, 2 to the 8 options of how you can rearrange these things. So that's a nice thing. So if we go to use an integer, so an integer is like first thing we're going to worry about. So what I'm doing here is meta level. Start sneaking you up on types, base data types in Julia, and things we might be interested in. So the most fundamental thing you're going to get are bits and bytes, right? They're just highs and lows on a computer, on some computer register somewhere in memory. Fine. We have an encoding to something we actually care about. So if we want to encode the integers with these 1s and 0s, trues and falses, maybe, whatever they are, high and low voltages, it's actually completely free. We could do whatever we wanted. We could have any random combinations of ons and offs turns into this number 1. Any other combination of ons and offs turns into 2. But it's not what actually happens. So don't know if we want to run this stuff, but so if we had 8 bits to represent integers, so we're back to some sort of primitive computer, and it's only got 8 bits represent 8 bits it can represent. So your computer now, assume everyone's on a 64-bit. Is anyone not on a 64-bit computer? So it still happens sometimes, but you get someone with a really ancient computer. Used to be a problem, but all the ones now are 64-bit. If you go to, like, say, an old video game console from the 80s, it would be an 8-bit computer. Then some were 16-bit, and that was like amazing. You've got this encoding problem. We're going to go. So if you've got 8 bits, you can go from 0 to 255 if you're worried about natural numbers. So what we call in computing these natural numbers is an unsigned integer. So there's no sign bit, plus or minus is the sign. In Julia, this guy's a uint8. So did you come across this? uint8? Did that come up before or not? Did you see? I'm guessing the types you would have seen, you might have seen int, and you might have seen float, and you would have seen string. So we're going to start from uints, so natural numbers. So how are the uints encoded? If you want help, Julia will tell you about this. So kind of unhelpful in this case. It's like uint8 is an 8-bit unsigned integer. Another one with Julia, when you're going there, just as a little hint, if you want to kind of fill in the rest, you can press tab if you've half typed something, and it will fill some things. So like you can see that there's this default one, there's an 8, a 16, 32, 64, and 128-bit. The uint defaults to your computer's native one. So if you're on a 32-bit computer, some reason, and you go uint, you end up with a 32-bit uint. Everyone else will end up in a 64. Possible source of bugs that could come up for you if you're running on different types of hardware. It's pretty weird to be running Julia on a 32-bit machine or a 16-bit machine, but it could happen. So with embedded machines and such. Yeah, so they're just different bit representations. So if you need on a really big number, you know, you can go that high. So I'll just run this bit of code. Any syntax questions as we go through? So we're going to go like, this is kind of redundant to go println n because it's going to, does anyone know what that /n symbol means? New line. So we don't really need that if we're doing println, but it adds a space. I think this is just formatting in the notes. So to put an extra line underneath. /t is a tab. So if you're doing it in, no, let's, anyway, blah, 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 blah. If you do println, you'll get a tab in between. So this is just formatting stuff, but it's good to see it. So you'll see it over here. It's going like println, unsigned 8 bits, new line. In the output here, it puts a space, and then here there's a space, tab, space, space, tab. This is just like, probably don't, that space is making me angry. But that's just to do the formatting. So not so important there. Probably more interesting here is we've got this for loop. We're going to go for n in 0 to 256. If n is less than 18, less than or equal to 18, and we know what this one is. Or cool, you're all with the basic Boolean stuff. And we've got a little hint here in the notes of like, if you want less than or equal /le, you can do that stuff, /le tab. And also if you want the GE greater than equal, you can do the GE. Cool, and that's a function. Cool. So this is just formatting so you get the ellipsis. This is what all this nonsense is doing. So if it's less than 18 or if it's greater than 250, we're going to print it out. Otherwise, we're going to do some dots, 3 dots. Else, if n is in 19 to 21, this is pretty yuck, but yeah, basically that's just to get these dots in there. So you can see that, oh, actually go to the meat of it here, is this guy, beat string uint 8 n. Oh, didn't say what n was, so 0, 1, 2, 3. So you'll be happy to know that the designers of computers back in the day, in their infinite wisdom, went for the obvious thing of just incrementing them in order. So they could have done anything. They went for in order. So yay, good on them. So that makes sense. So like, it's just the binary representation of numbers. It's just counting in base 2. It's goes 0, 1, 1, 0, 1, 1. 1, 0, 0, 1, 0, 1, blah, 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 blah. What's going to happen if I do that? Error, yay, because it's not happy to do that. So that's good. Catches an error. That's what we want. It might, yeah. If we add, though, that's where things get interesting. So in terms of, anyway, back to the point of the lecture, could have been anything. They went for the obvious thing. There's this other thing called hex, base 16. It's got hexadecimal representation. Sometimes it's useful because of bits and bytes. You know, you want to go to have a representation in terms of base 16 numbers. So that's something they've decided to do. This is this base equals 16. If you want to see what that is. Okay, cool. Now is where stuff gets weird. Okay. What happens if we want to do signed integers? If say we want to go, we're crazy people and we want to go negative. How would we represent that in bits? What would you do? Anyone want to say what they would do? Yeah? At the front. Yes, do you think they did that? No, they did not do that. Why? So, you know?
Like the maximum range of numbers that you can store is greatly limited.
Is it? So you got 1 bit for the sign, and then you got 7. So how much? What's 2 to the 7? Yeah. So still get the same range-ish. Maybe lose 1. Yeah, lose 1. It's like, you know. Yep.
It makes like any arithmetic of what easier to compute.
Yep. So we're going to get to this in this lecture. So this is a bit where, for anyone who's a bit newer to programming, this is where it's going to get a little bit hairy really quick. I'm going to show you why, or one reason why, a good reason why, but it's going to get complicated a little bit quick, but there's a reason for this, and hopefully you can see it. So yeah, so what they do, so this actual encoding is they start, the -128 is 1, 0, 0, 0, and then it increments up to 0, and then clicks over to 0 and starts going again. It's actually kind of curious, right? Like why you would do that. As for a beginner, you look at that and you go, huh? Like just have a sign bit, it's fine. Or just offset them all or something. So it's kind of confusing. Yeah, so 2's complement. So well, that's just a little puzzle. Later in the notes, I'm going to go through why this particular encoding. That's where this lecture will get a little bit harder, hopefully not too hard, and we can go a bit slow if you want to go through it. So base 16 is a thing you might care about too. Hexadecimal, that's what I was saying. You often see this if you do something like a hex dump. If you're looking at a binary file, you look for special magic bits to see what's going on in the file. Hexadecimal uses 4 bits, not 8. And so a byte will typically be 2 hex digits together. So if you want to do this, in Julia, you get this little OX thing. Has anyone seen this? OX1. So that's a uint8, but we can put hexadecimal things in there. So lots of different ways to skin a cat. We've got a little bit more syntax here. We've got latex strings. Don't worry too much about that package. That's just for pretty formatting. But if we want to put hexadecimal in, we can put this little OX in here. So you might have seen one that will be more familiar. If I do 1e to the -6, has anyone seen that before? What's that going to do? Like scientific notation, right? You go like, oh, it's 1 times 10 to the -6. What type do we think this will come out as? A float? Any particular type of float? What do you think? Float 64. So there's all these little shortcuts you can do though. I can actually do that. It's like, it's that guy. That's a float 32. If you want a shortcut for making a float 32, one for hex is this OX. So you can go OXE, type of, it will encode, oh, Jesus, is a uint8. So if you want a little shortcut for making a hex thing, you can put that in there with this little OX. Similar trick you can do for, there's not the ones you will have to know. You've got E, you actually already knew that one. F is another one you might want to see if you want a quick little constructor for a float 32. You'll have OX for these, for the uints, and OB for binary ones you can do as well. So you don't need this stuff, but I'll just have it here because Yoni has a habit of putting them in the quiz. So it's good to know. Yeah, cool. So what we're doing here, we've got some data that's like 0, 1, 2, 3, 4, 5, 6, 7, and we're going to print that guy and what it is in different bases. So hex is this 0, 1, 2, 3, 4, blah, and decimal, that's the decimal representation. So where have we got that guy happening? So digits, print hex and decimal. Yep. Cool. All right. Yeah, so for binary, just said that one. So we can go, if we do x equals 11, type of x is an int 64. We can also go, so in binary, as I said, the 0b, we're going to go 1, 0, 1, 1. So who can count in binary? What's that going to be? Is x equal, is this actually true? It's true, but just different representations of the numbers. So X is in, so again, we've got different types, but the value is the same. So that's just 11 in binary. As a hex string, it's OB. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, AB. So that's why it's come out as this OX. So they're the same thing. And you can do arithmetic in bases. So this is the kind of stuff I want to copy. So again, so if you want to, you can add these things together, that'll make sense. And a bit more magical. If I have this guy will turn into, sorry, I should say what the type of this guy is. That's another uint8. That's another uint8. So they're just different ways of getting them into the type system of Julia. They're ways for you to express this number and type them in. So little bits of code there. Can seem a little bit mysterious. So, yeah. Here's the interesting stuff we want to do. So if we're going to go, this is the one where I said, oh, what's going to happen if I do this cheeky thing where I go like, I'm going to do this guy, it's going to go no error, but I can go 255 plus uint 1, uint 8, 1. Oh no, what it actually did was if I stay in the type, it comes around from the bottom. So that's something to keep in mind. So we've got these examples here. So if we add 1, we're going to get wraparound. And for signed integers, 2 at 7. Comes up from underneath to minus. So as you add 1. Something to keep aware, this is a bug. So we're not, first, as I was saying before about we've got these computers of this bucket of leaky abstractions. It's not really a natural number. It's really 8 bits. And so if you try and do something, the arithmetic's going to be a little bit weird, more like modular arithmetic, where it's going to click around and do strange things that you're not expecting. It's not really an integer. So even when I'm using one of these big guys, though, if I'm going like if I do an int, like just a random integer, that has 64 bits. So the same thing will happen if I go to the type max. So useful function, surprisingly useful, is int 8, type max of int 8. Similarly, we have the same thing for 64-bit. So it's just a much bigger number. So, you know, if you need more precision, so this is when, if you're starting to do simulations and stuff, it will come about when you're doing computer algebra. That's why you've got in your homework, it'll say about big floats and big ints and stuff. If sometimes, particularly the computer, when you get Paul Verbeek's section, it's really easy for the numbers to get really, really big, really, really quickly when you're doing that sort of stuff. So you need these different types where you've got arbitrary precision. So that's a pretty big number though. So, oh yeah. Pretty much. It's like until it's kind of fill your boots until the RAM runs out. So they're arbitrary, except your computer's real. Maybe if you had some swap thing and you could memory map it. So people who do crazy stuff like the computer science people doing factoring primes and stuff, very, very big numbers, they probably have special representations for dealing with really, really big numbers. Don't actually know much about that. It sounds kind of interesting though. So yeah, they'll be doing clever things. So that's a big number. So we saw this, cool. So unsigned integers wrapped, got too big. The other one wrapped around and came back down to minus. And yeah, you can do the same thing can happen for the bigger ones. Okay, this is where there's more syntax here. This is some yucky stuff I wrote, so blame me. We're going to go a little bit harder about why we would use this particular encoding of integers and why that's a good idea. Question is, how do you add? Okay, so I think I want to go just on this bit here. Okay, we've got a really hard, challenging problem. We've got binary numbers. We want to add either 0 plus 0, 0 plus 1, 1 plus 0, or 1 plus 1. That's it. So we're just going to enumerate all those cases. So what's 0 plus 0? So what's 0 plus 1? What about 1 plus 0? And what about 1 plus 1? 1, 0. Yeah, it's there. It's on there. It's 1 carry the 0. So like you can't represent it in 1 bit. So you need to carry something over. If we look at the pattern on this side for the carry bit, cool. What pattern does that look like? And hopefully that's clear. That's why it's written over here. You'll notice like if you go through all the cases, and looks like the carry bit. What about this guy? We've got 0, 1, 1, and 0. Exclusive OR. Has anyone heard of exclusive OR who's not done programming before? Did that come up with Yoni stuff or not? Was he good? And exclusive OR. If you've done logic, you will have seen that. So that's this thing. It's like if it was OR, it was just a normal OR, that guy would be a 1, 2, but this special thing called an exclusive OR. So if you've got 2 bits, you can add them with an XOR. That's all you need. So what I've got here, now I'm going to encourage you to go through this yourself and pull it apart. What I've done here is I've done this inline function called a half adder. So it's called a half adder for reasons, but this is basically exactly what I just said. So half adder with some weird stuff. Has this come up before? Have you seen this little weird syntax? And you go, God, there's dots and stuff. Haven't seen that? Okay, so that's cool. So what I've got here is this is a thing in Julia that'll come up. I don't need to do it here. I just wanted to put it in here so you could see it. And when you actually need it, it won't shock you. This function will work just fine if I delete this stuff. Absolutely fine. So this is this inline function, as I said before. We could write this out long-winded. What I'm doing is if I take A and B, I'm going to return a tuple of an XOR and AB and A and B, just what we just said. I wrote the diagram in 5 seconds, so can be any way. You just have to know which is which, right? Like, so this is the thing. So probably an example where you're returning, like before, I'm returning multiple things. And so they have there's an ordering that's going to matter when you're worrying about what the return type is. So when you call this function, you need to know first one means this, second one means this, or you're going to get an error. Normal sort of bug stuff you'll get in programming. So is that clear? What I'm actually doing here, though, is I'm giving it a hint about the type. So I'm saying this is called type annotation. And you don't need to do this in Julia, but it can help. You don't need to do it in general. But what happens if I try and run this function on things that aren't Booleans? Does this make sense? If I've got like A is a string and B is a file path to somewhere, if I try and AND those and XOR those, does that make sense? Well, if I don't, it might do something exotic. Like maybe those functions are defined for those types. I don't know if they actually are or not. Like you would have seen this. I can totally do this, where it will be string concatenation, whereas I'm expecting multiplication, right? Like if my function, I'm thinking these things should be multiplied, and then it's going to do some other overloaded thing. It's kind of bad. So this case, this is pretty. It's not a good use of this, but basically this is to catch that I don't want you to use this if the types aren't Booleans and throw an error. There'll be a method error. This is like the most common bug you'll see. Has anyone seen method error yet? Do you know what it means? Kind of. Yeah. So it's a good thing to know. So like, it's actually, that's what it means when you get this method error. It will say, the error logging is a lot better than it used to be, but this most common error you'll get in Julia is a method error that this particular thing won't happen. Sometimes you want that to throw on purpose because it'll catch a bug. So if I write some complicated thing deep down in my function, I'm expecting this thing to be a Boolean and this thing to be a Boolean. If I apply this to this and they're not that, I want it to throw an error and go like, no. Otherwise the space shuttle crashes and horrible things happen. So this is just a little bit of type annotation to go like, okay, so true, false. So we should be able to just enumerate the cases we just did. So false, false, true, false. It's going to get tedious really quick. Sorry, I did this. And true, true. Cool.
So, sorry. Just to find.
It's saying it should be a Boolean throw if not. This is only defining a method for Booleans. So that's what this where syntax is. So A is of type T, where T is a subtype of Booleans. So this little funny symbol here, again, if you don't know, subtype operator. So for example, int is a subtype of number. String is a subtype of number, no. So what this little bit of yucky syntax, just trying to scare you all, is saying A, oh, touchscreen, A is a subtype of the Booleans and B is a subtype of the Booleans. And then we're going to return this tuple XOR and A and B. That's a half adder. So that's if we're adding 2 bits. 2 bits. And we've got this carry bit. Now, exercise left for reader. We want to do this again, but we have another column that's carry. What's the carry? What's it going to be if I go to the next one over? So if I've got A and B carry 0, 0 and 0 carry 0, what's the result going to be? 0 and 1 carry 0, what's the result going to be? You can fill out this table and make the same equivalent truth table and work out what that is. That would be what you need to do for the next one. I'm going to leave that for you guys to do yourself and just tell you the result. This is called a full adder. So what I've got here is I've got A is of type T, B is of type T, and carry is of type T, where T is a subtype of the Booleans. What the magic result is we can work out this. Well, you can use 2 half adders and combine the results to give us the full adder result. A carry bit. So if I go like, 9 plus 7, and it's going to be 6 carry 1, like in base 10. You have the same thing in binary. If you go 1 plus 1, it's going to be 0 carry the 1. So when you go to add it to the next thing, you need to worry about that carry. So just imagine you're doing the arithmetic like you would in primary school, where you're going to go like, 7 plus 9, 8 plus 3, you have to carry across. That's what I'm mean by the carry bit. Sorry, I didn't explain that. That's would have been mystifying. Does that make sense? Think so? Sorry, I couldn't hear that one. No, that's just a variable. So again, remember this guy is returning the carry bit in the second position, and it's returning the result underneath. So imagine you're doing this addition. It's like you want to put this guy in the first spot and then this guy in the second spot. So this is the carry. When I'm returning stuff, this is the bit that's carried from the previous addition. Could have chosen a better variable name. I'm sorry about that. Does that make sense? So as a result, I'd leave this for you guys to do. You can make a full adder from 2 half adders. So why would we do that is, this is actually a circuit. On the computer, all it can do on the CPU is logic. So if I can compose bits from the same bits, I get reuse of things. I can use the same circuit twice. So a half adder and a half adder, wire them together with again, that's an OR. I will get the correct thing. So that's a full adder circuit. So what this thing is actually called, when it's implemented in hardware, is called a ripple adder. So you go from left to right, adding, carrying, adding, carrying, adding, carrying, adding, carrying. You can make that from 2 half adder circuits, put those together with a logical operation. So then that's a way of doing, if you have this particular representation for integers, for the unsigned integers, this addition method will work, because we went for the obvious way of encoding the binary numbers. I can do this little simple circuit and this little simple circuit. And what I'm going to do here, take two integers, convert them to Booleans, And this is kind of gross. But you imagine inside this thing in the CPU somewhere, there's an arithmetic unit that has to add binary numbers really, really quickly. It's going to be implemented as logic gates. So I've gone way up this pile of abstractions, and I'm doing it in software, what it's probably kind of doing in hardware. And it's this ripple adder thing. So what I'm doing here is we start off with carry. So what this guy will do so A was just a number, and n equals 16, say. So that's just like that bit string thing we had, big bit string function we had before. It's just another way of doing it. You can do things multiple different ways in different languages. So we had this bit string thing. And what number was I doing? 12. So hopefully you see the same thing. It's 0, 0, 1, 1, blah, 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 blah. This is 0, 0, 0, 1, 1. So what I've done with this function is I've made a vector of Booleans that is the binary representation as a uint for the number 12 in base 16. So what I'm going to do though, I can go through this vector from left to right, running this full adder, and it will give me the result. Yay. So that's the ripple adder. So if you wonder, possibly, how would you do it in a hardware with just logic? That's where we're starting from. So all a computer can do is logical operations. So we've shown here for 1 bit, if you're not worried about a carry bit, you can do it with an and and an XOR. If you're worried about the carry bit, this is a bit you can go home and think about yourselves. You can do it with 2 half adders. And what you have to do is all the results together and get this funny thing S and just pass it through. So again, only logical operations to here. And what I'm demonstrating here is like convert this number in its base representation to an array of Booleans, go through that array one at a time, adding it together. Cool. So results. I won't bother running it, but I would encourage you, what I'm doing here, where I'm going, if you see a thing and you don't understand it, copy it across into a REPL session, put numbers into it, pull it apart, see if you can make it error. I would completely encourage you to do it. I'd be super happy if you run this function and you break it for me and tell me I've done the wrong thing, because that would be good. So I've probably got a bug in there somewhere. So what we're going to do, yeah, is we're adding these things with just logic operations. That's kind of cool. So the magical thing, all the way back to the beginning. So hopefully, if we go A equals, we're showing there's a result. If you go 1 + 1, you get 2. Woo. Magical thing though is this circuit will work for uints and signed integers if you do 2's complement. So I can use the same circuit to add uints and signed ints if I do 2's complement representation for signed integers. It won't work if I do this. There's a signed bit out the front. Does that make sense? I lost anyone? Yeah. So this, we went back up to the front, back up to the top here. Why did we choose this funny encoding? It's because that circuit will work on it too. So this is an example of like, why did they choose this particular representation back in forever ago, 1950s or whatever? I think it was when they were, maybe in the 1940s, they were trying to work out, there used to be a thing called 1's complement, and then they've gone 2's complement. 2's complement works because it optimizes the hardware. Isn't that crazy? Cool. That's an algorithm for doing addition. Is it the best? As a question to the floor. No? Shaking your head? Yep. Yeah, you're actually, it is that ripple ladder. So what, if I think about how many operations I have to do for this thing, if I've got a bit string that's like 64 bits or 16 bits, how long will this operation take? How many different logical operations am I going to be doing? Yeah, so it depends on the length. Cool. That makes sense. So can someone suggest what you might do differently? What would that look like in this case, adding them in parallel? Yeah, or another thing you could try and do is chunk the things. There's no reason you just have to add 2 things. You could add groups of 4 or groups of 3 or whatever you wanted. You could chunk it up that way. So in terms of like what's optimal, it's kind of a hard question. You get to this point where you go, oh, that's actually kind of confusing about like, if I was trying to minimize the number of logical operations I was going to do and minimize the time as well, it kind of gets confusing about what the best way to do it is. Okay, so I say when we do adding, we do the primary school algorithm where we go, if we're going across, we're going A plus B, carry. What about multiplication? How would you do multiplication if you were going to do it with just logic? Yep. Yeah. So what about if we're doing integers though? Like how would we do if we've got some integer representation? So what's the primary school version algorithm of multiplication? How many steps do we have to do? So we're going to go this plus this times this times this times this times this, then put a 0 and go again, and then add them all at the end. What does that scale like compared to addition? Is that better or worse? What's that? Yeah, so that's kind of like, do you think that's a problem or not a problem? Yep, cool. So not going to do that here, because I think that's traumatic enough to go through the half adder, full adder, ripple adder thing. But trying to give you a hint about this idea of computational complexity. This will come up in the next section more. We'll talk a little bit about it more in the context of sorting, but I want to kind of click your brain on like this algorithmic thinking and computational complexity and how you might optimize this. And this algorithm works, but is it the optimal algorithm? What does optimum even mean? When you have different problems, how do they scale with the size of the problem? Because this is really the nice bit of computer science mathematics that people do really well with this sort of background. And this is like the first hint. So we've seen for this implementation of an adder, you know, it's linear, that's pretty good. Scaling like the square is kind of bad. When's it going to be really bad? Yeah, so like if you're going big ints, right? Like if you're doing, when you get into this next bit where you're doing polynomial, if you're doing polynomial multiplication and you have very, very big coefficients, that's actually going to be a problem. So I think the magic algorithm, does anyone know what it is? Has anyone heard? So Karatsuba's algorithm is the one for multiplication of integers, and it was only invented in the 60s or something. And I think the guy was a Russian guy. I just think his name sounds Japanese, but I think he was a Russian guy. Yeah, cool. Any questions on that bit? That was the bit where I was a bit worried I'd lose some people, and everyone's sort of happy. Main educational point is though, we saw there was something weird. There was a reason something was weird, and it had to do with the lower level stuff going on in the system. So we do this slightly strange representation of unsigned integers, or signed integers, sorry, so that we can reuse the same bit of hardware. The same sort of hardware will work. Cool. Okay. Whew. I think it just kind of jumps back to stuff that's a bit less interesting. Yeah, so we went through that. I'll go through this one. So we won't worry so much about that one. Yeah, bit shift. So again, low-level operations. We have OB101, 5. Okay, so when you go, like the easiest thing you could do on a computer is you could just shift things left or right. So this little funny operation here is called a bit shift operation. So again, if you need help, this is the left bit shift operator and the right bit shift operator. Oh, that one though has more methods associated with it. So this guy only gets, oh, sorry, I didn't do the help. Yeah, right bit shift operator. So if we have a number, we did x equals blah, we can shift it to the left and we can shift it to the right, which isn't so useful in this form. So if we do, this is what we want though, bit string of this guy. So this idea, really simple thing to do in hardware is just take everything, move it one way. You want to move it 2, you want to move it 3. They'll kind of disappear if we go too far off the other side. Cool. Yes? No, just disappears off the back. Yeah, it's not a cyclic bit shift. It's not a cyclic bit shift. It's just a shift and things disappear off the side. So thing to keep in mind. That's that bit of thing. Now, who's either read the notes or is super cluey? Why would that be? Why would we care? What's that equivalent to doing? Yeah. Because if you think about binary representation, it's powers of 2 each one. So if you're thinking of the encoding, it's going to be like, you know, how many powers of 0? 1, 2, 3, 4, 5. So every time you're shifting, it's like a really fast way of, this is like never comes up for me. Professional career, I think I've never had to bit shift anything ever. So I don't really work at that level. But if you ever really, really need to do a fast division by 2, you can go this guy, bit shift. Yeah, so anyway, blah, blah, blah. That's more stuff of that. So I think little bits of syntax. Did you see we can go? Yeah, I'm trying to think about what's important to show you. Another one I think is actually important is we can do. So if I do normal divide, what's the type of this guy and this guy, 4 and 2? What are they going to be? Yep, in 64. So just if you don't believe me, type of 4 is in 64, type of 2. Hint there, what do you think the type of this guy is going to be? Float. Yeah, you get the hint because it put the point there, but yeah, it'll convert it to a float 64. So this stuff about conversion and promotion of types kind of happening magically. This is like maybe your first example if you're seeing it. If you really don't want that to happen, you can do an integer division, which is this guy. This actually makes, what's going to be the type of this guy? Or what's this function? Divide 2 numbers or rational numbers. So this, sorry, I said the wrong thing, but kind of giving away the thing here. You can actually represent a rational number. So we don't have to give anything away. So floating point, we'll come up to this in floating point. I'm not going to talk about too much early on. I'll come back to it later on. I think, I can't remember which section I do it in, but definitely it's probably the next one I talk about float in detail. Floating point is the next thing we probably want to talk about a little bit. I'll give you a little hint when I talk about one of these first algorithmic things we're going to go through, maths algorithmic things. Floating point's only an approximate representation of the real numbers. It has issues with representing numbers. If you're doing a division, you don't need to do that. You can have a rational type that is exact, as long as you keep it. Anyone like, does that sound confusing? Or it's okay? How might you store a rational number? Like if you're going to make a type yourself? Yeah, that's right. So you could go struct, making a type myself for the first time. Did you only show you this at all, or this is the first time? Can't be bothered typing it all out. So I can make my rational, but there's no methods associated with my rational. If I try and go Oh, sorry. Method error, that was the one I was talking about, because there's nothing defined for my type. I have to go and define a bunch of functions so this thing would actually work. Whereas if we go back to this guy, it's already built in. So this should work, but what's the type of the return now? What's happened to it? It's a rational, it stays in the rational type. So you might have seen, did you only show you one with complex numbers? A little bit? I'll show you complex numbers, that's fine. First example of like, there's higher order concepts you can make from the low ones that are useful in certain situations. If you're a rational and you're staying in the rationals, all your results are going to be exact. There's no approximation involved. As soon as you go to floats, which is if you do this other type of division, it's when you start to get interesting things. You can also do div, which is more like your quotient from Euclidean division, equivalent mathematical quotient without a fractional part. Whole bunch of those sort of things. There's also, they'll do the same thing. So if you really like that one, you can do that. Cool. Yeah, so bit shift, like powers of 2, like dividing and multiplying by 2. This is all back to basic stuff. So useful thing again, although it lies to you, is size of. So what this will do is give you the size in bytes, not bits, of the type of the thing you're putting in there. Cool. So this one's, so size of, so again, got to hide the notes so I can actually ask you questions without seeing it. So if I go uint 8, or sorry, assigned int 8, what's the size of that going to be in bytes? 1. So pretty boring. 16, 32. Int. Cool. That's pretty much that. What about 4.0? 8, yeah. So this is all too easy for you guys. It will lie to you though, so I wonder what will happen if I don't actually know what it's going to do. What do you think it's going to do if I do that? Yeah, it's still U in 8s, like we were saying. So your guess about just having a numerator and a denominator, primitive types, it's gone, oh yeah, cool, there's an 8 and an 8, so 16. What did I do? What's this going to do? I think it's going to do a method error, but we'll see. Oh no, it did. Yeah. Good. Okay, so what about, so if I said another basic thing, which is what we will get onto next, is a string. If I say a string, what about, are you happy with what that means or not really? It's like list of characters. So if I go, maybe I should pick one that's like, just pick a word. So size of X, what do we think that's going to be? Divided by 8, yeah. So 8 bits for each one, 8 bytes, yeah. So size of X. So yeah, so well, each one is 1 byte. So if I go X, this is going to be a little bit weird. What does it do? What does it mean if I do that? What am I doing? Yeah, so it's like you can think of it like a list of characters, and I'm getting the first thing in the list of characters. So you'll get a hint about what's going on there. It goes like, oh, it's this H is an ASCII Unicode, blah, 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 blah. Category L1, letter lowercase. Cool. Makes sense? So strings, as we said, that's a bit more like this arbitrary case, right? Like when we're saying like ints, there's like a thing that you go like, yeah, if you didn't do that, it's weird. You should go 0, 1, 1, 0, 1, 1, 1, 0, 0. Strings, it's like A, B. How are you going to encode that in bits? Like you could do whatever you wanted, right? So the notion of closeness in bits doesn't really make sense for strings. Like each one's kind of like a different thing, right? A is only closer to B in this particular ordering we chose for remembering the alphabet. They're not actually close to each other. Yeah. Yeah, it's the size in bytes of the representation. So sorry. Let's go back up here. So size in bytes of canonical binary representation for a given data type T. So for the particular instance of that thing. So what we're going to do when it goes a little bit weird, oh, you can probably see the answer. So we did size of H is 1. What happens if I go alpha? What do you think that's going to do? 5? 2. What happens if I go? No, it's not there. Can't remember the Unicode stuff. Anyway, I won't do that. Yeah, so you've got a character set. So there's basically just a mapping and there's different tables of these things. That's what this ASCII stuff is all about. There's some committee somewhere decided there's ASCII. Have we come across that before? First time? So you get 8 special bits that represent a set of 256 characters. And if you want more, you go into Unicode, which there's an 8-bit and a 16-bit versions of Unicode. Because this is a special Unicode character, so we'll see this one before. So I'll go, this guy is Y, and this guy is X. So I go Y1. You can see that's ASCII, Unicode, blah, blah, blah. But if I go X1, it's not the ASCII bit. It's just goes straight to Unicode. So that needs a bigger binary representation because it's a larger character set. So if you're going to go, actually have a friend who worked on this as a bizarre application of like mapping characters in languages. I think he was doing Cambodian for translating books. So the character set's not necessarily always there. So there's like letters still that aren't, I think the coverage is pretty good these days, but different programs will have different levels of completion of like the character sets they're going to use for different languages. So if you move out of the larger languages to smaller ones, there's still things where it's difficult to have representations. So Unicode project is a big deal. Cool. So we'll go for an easy one again. Anyone seen this function? Ones? We've seen that before? No? Cool. What do you think it might do? Yep. So it'll make a vector of ones. So another useful one, zeros, make a vector of zeros. You'll notice that it defaults to type 64. So if you want to make int 8 or int 8, you have to give it the type first and then how many. So you've got zeros, ones. So what do we think size of this thing's going to be? If it's int 8 and there's 5 of them. Beautiful. 64 is 40, blah, blah, blah. Make sense? I'd say it's a bias towards numerical computing. So like the same as RAND, like why does RAND default to uniform floats? It's a choice in the design of the language that most people who are going to be doing this are going to be doing numerical linear algebra probably. So that's a sensible default, I would say. Yeah, cool. See if we've got any hairy ones there. So, oh yeah, so we did floats. Yep, so again, you got different floating point representations, blah, blah, blah. Yeah, cool. Okay, So I'll spend the last 5 minutes probably talking about Julia itself. This course isn't a Julia course. It's a course in Julia, but it's kind of useful to talk about Julia and where it's coming from. I guess, did you only do a hello world for you and seen all that stuff, or not really? Do you want me to do another one? But basic ways of interacting with Julia, you would have seen. So using a terminal, you just start Julia, blah, blah, blah. It's completely possible to, let's make a little file, new text file. Don't need this, but it just makes nice syntax highlighting. So x equals 2 plus 4 println x. I'm going to save this as so I'm going to make just a little text file. So text editor, VS Code. Has everyone installed VS Code, or is anyone using anything else? Anyone chosen something exotic and Neo Vim or something? Notepad++, go for it. Yeah. How about you? Yeah, so this is one maybe for people newer to programming, is like a program at this level for these languages. It's just a file. It's just a text file. This VS Code, if it seems intimidating, it's just a text editor. You can totally use Notepad, or if you want, Notepad++ is a better deal. You can use, there's a whole bunch of editors. If you go on to, you could use Vim. I used Vim for years. So what I've done is I've just made a little, oh, this is way too small to see. Okay. Appreciate that now. Terminal, new terminal. So you can go Julia, and I can go x equals 2 plus 4. I can go println x. Cool. I don't need to go into this thing though. I can just go. I can just run the file from Julia. So you don't need to go into the REPL. If you want to write a big program, you know, this is what you do. Like in my professional work, this is the way it's always happening. So I'm writing it with an entry point. I'm not mucking around in the REPL. I use the REPL for development. You just make a file. They're all just series of files. Python's the same, you know, it's just a bunch of folders and files. Nothing too complicated there. So I don't know what else I want to say. Yeah, so where Julia came from is, you know, I was saying before, you've got the kind of like two types of developers. You've got like these hardcore software engineers who are doing stuff like who knows what, like wiring APIs together. And then you've got like more mathematical developers, I would say, who are kind of a confused story. And it's like, it was a huge problem for us when I worked at Fugro that we'd have these people with like maths PhDs and getting them to work productively so they can do problems that the other people can't do, but they can't necessarily write the software to run. So having this kind of two worlds, and the old school way of doing it was probably right. You prototype it in Python and then find the slow bits and then rewrite them in C++. And C++ is a lot less friendly. Any C++ developers? Anyone had a go? Ages ago, yeah. Mostly around memory management is the thing where you'll come unstuck. So it's a lower level language. It's still a high level language. We'll talk a little bit more later on. I'll show you some examples about what actually executes on the computer. I'll show you some machine code. We can do that in Julia, what actually gets run versus what we write. And there's like a level of abstraction. So these people working in the 50s were writing basically, how do I flip the bits? Like it was at that level. You don't get for loops even. You know, for loops are a higher order construct. So they're not real. There's nothing in the hardware that's making a for loop. That's all software turning into things that execute on the computer. Anyway, lower level languages tend to be much faster. Much faster. So if you really, really, really care about performance, it's like nobody does this these days, but do something in assembly. These days, it's like Rust or C++ or Zig or something crazy like that. It's all these fast Golang maybe. Then you kind of go up into the fluffier stuff. And the way it was historically was scientist types would work in the higher level languages because they're more worried about higher order concepts of you know, just getting the maths right, not so much the implementation. That was a huge problem for us. So you saw what have seen in Megan's talk, we were doing huge point clouds. So when I left, it would be interesting, did Megan say how much data they have? What's that? I think the data capture rate we had from one plane was 100 megabits a second. And we had 4 planes running for 8 hours a day when I worked there. Yeah. So we literally had a ton of hard drives getting couriered around Queensland when I worked there. A week. Every week, the hard drives, we'd ship them in, put them in thing, fast pipe up to AWS. It's like crazy. So like the cost of shipping data around was a huge cost for us. It's kind of crazy. And so I don't imagine now, if you go back in time, you can ask Megan, it's probably worse now. We had over a petabyte of data when I left in AWS. So our AWS bill was like, ooh. Anyway, big data sets from LiDAR generate lots of points really, really quickly. Trying to do complicated things like finding geometry in the point cloud is like difficult. It's a hard problem. Like it's not a simple problem. Did she talk much about that? Like point filtering and stuff? Yeah, cool. You all know more than me. Yeah, so like we had a huge problem of like people working in, say, productivity languages, R, Python, versus C++ developers, and having a reconciliation between these two. So that's really where Julia was born. And it was kind of a crazy decision from Claire and myself to actually start using Julia when we worked there, and it's kind of kept on going there. It's like, ideally, it's this thing of trying to match up performance and expressiveness and nice, easy language. That's where it's coming from. I'd say it's not as friendly as Python. Has everyone found that so far, or not really? Haven't seen it yet. Well, you'll see it. It's like, it looks nice and then it has its rough edges, but that's where it's coming from. But it's a good language. Yeah. Does anyone like use notebooks? Do you like notebooks? Anyone else? I personally have never got on with, because I'm useless and I get the code cell execution wrong and I end up in a weird spot and have to kill the kernel all the time. So I actually don't like them. And has anyone, your IPython or your IPython notebooks, I guess they're Julia notebooks, whatever, using them in Git, have you had problems yet? With the contents of the cells? Yeah, so maybe you want to clear your cells before you go into Git. Like, I don't know, for the homework, are you gonna, I'd say like the easiest thing for you to do is to just like interleave your questions and then merge it later on, like just by files. But you can, the problem is like, we'll talk about Git later on. I'll give you a bit more of a hint, but yeah. Anyway, I don't actually use notebooks. My whole life is just like VS Code and REPL. That's how I work. Cool. All right. Any questions on this stuff? Catch you again tomorrow? Yeah. Yep. Okay, thank you very much, everyone.
The legend of Gandhi and civilization.